It's my pleasure to introduce Professor Ning from Princeton University, where she's an associate professor in the Department of Civil and Environmental Engineering there. As you'll hear about today, she focuses a lot of her research on hurricane hazards, whether it be wind, storm surge, heavy rainfall, and focusing not only on the current, but also the future, especially as it's applied to coastal resilience and other applications. She's published over 90 papers, many of which are in very prestigious journals dealing with various interdisciplinary type of applications. She's won numerous awards, such as the NSF Career Award, the Natural Hazards Early Career Award there at AGU, and also the Global Environmental Change Early Career Award there at AGU. So it's my pleasure to have Ning join us. Actually, she's not feeling too well today, so I really appreciate her doing this under the circumstances. And so I'm looking forward to your seminar, Ning. So if you don't mind sharing your screen.
Sure. Thank you, Brian. Thanks for the introduction. Thank you for inviting me. It's great to talk about my research on hurricane hazards and risk, and hopefully get questions and feedback from you all. As Brian mentioned, I've been working on various kinds of hazards from tropical cyclones and also other associated hazards. And particularly how these hazards and risk will change under climate change. So just a very quick introduction to get everyone on the terminology. Hurricanes are also called tropical cyclones, or those tropical cyclones, when they become strong, they are called hurricanes in our region in the North Atlantic, but they're called typhoons in West Pacific, and maybe they're called a severe cyclone storm, severe tropical cyclones in other regions. But basically, they're physically the same. So we generally call them tropical cyclones or TCs or hurricanes. As you can see, this is a global phenomenon affecting many coastal regions around the world. So this is a satellite picture of a tropical cyclone. You can see that it has a visible eye or low pressure center and a very coherent structure for mature tropical cyclones. And this is a profile, a cross-section looking at the structure of the tropical cyclones. So this, the air at a lower level, about above of the boundary layer, about 1 kilometer, will move counterclockwise in the northern hemisphere and spiral towards the center of the storm, and moves up along the eye walls and these ring bands, and then become strong rainfall and the strong winds. And so this low-level wind above the boundary layer may be modeled with a simple wind profile, which says the wind will be approximately 0 at the center, and then will increase to a maximum wind at the radius maximum wind, and then decrease quickly to 0 at the storm out radius. And also the intensity is described not only by the maximum wind, but also central pressure. What's the difference between the pressure at the center and the environment? So those are kind of the storm parameters. If we know this kind of parameters, we have theoretical wind profiles to approximately describe such a wind profile of tropical cyclones. So tropical cyclones bring us extreme winds. As we know, category 1 to category 5 is based on the wind of tropical cyclones, but they also bring extreme rainfall. This is a map for over Houston during Hurricane Harvey. And the extreme winds can push the water to the coast, inducing storm surge and waves on top of the storm surge. And those surge will be above the astronomical tide. And the combination of surge and tide is called a storm tide. And storm tide, on top of that, we have wind waves causing damage to coastal structures. So hurricanes produce multiple hazards. And if they change in the future climate, these hazards will all change. And if sea level increases, the baseline of storm surge flooding will increase. Also, these hazards, not only we have multi-hazards, we may have compound hazards from tropical cyclones. For example, compound flooding induced from riverine flooding, rainfall flooding, and storm surge simultaneously or sequentially. This figure shows correlation of surge and precipitation for New York in different ways of characterization, but just focus on the highlights here. The squares are from tropical cyclones. As you can see, in tropical cyclones, surge and the precipitation are highly correlated, and they determine the tail of that joint probability. And this figure shows this correlation between rainfall and surge over time in New York, and it's been shown that it's increasing, has been increasing over time. So this compound hazards and compound flooding from tropical cyclones is an important topic for research. We always see that hazards will not become disasters unless they meet the vulnerability, right? So recent hazards events, tropical cyclone events have again show us that our coastal areas are vulnerable to such hazards. Although we have improved in terms of warning and preparation, and we have greatly reduced the fatalities in recent decades and years, but economic impact is still very high. And most devastating hurricanes around the world are actually in the United States. Looking at the time history of the economic losses from tropical cyclones, there's a trend of significant increase of economic losses from tropical cyclones. However, this trend actually largely induced by the coastal development, population growth in the Gulf of Atlantic Gulf regions has been going up steadily, regardless of the occurrence of these tropical cyclones and hurricanes. So when you normalize these economic losses, considering the population growth and coastal growth and inflation and so on, the trend is gone. So climate change effects in economic losses of tropical cyclones has not been detected in the historical record. However, in the future, tropical cyclones can change, and maybe the impact of climate change will stand out more. Just look at how TCs has been changing, the world change. Although we have limited historical data, studies have shown that the proportion of major tropical cyclones have been increasing over the past decades. Cyclones entering coastal regions have been increasing over the past decades, and those are the ones that are causing the damage. Also, study shows the time for tropical cyclones to decay over land has been increasing over time, although there's other studies shows that this trend is quite uncertain, given the limited historical record. A lot more studies have been looking at the future. Various climate models have been used to project future changes of tropical cyclones. This study had a summary of how many models or studies have shown the percentage of change of tropical cyclones in the future climate. And most models have shown that the intensity will increase in the future climate. This figure shows that most models predict that overall frequency of tropical cyclones may be decreasing in the future, but a few models actually predict that its frequency will increase in the future. So how storm frequency, tropical cyclone frequency will change under climate change is a big uncertain factor in our risk analysis. But keep in mind that the frequency of most extreme events were likely to increase, and those are the ones that are causing most of the damage. So my research question has been, how can we quantify TC risk in a changing climate, and how can we better mitigate the risk and adapt to climate change? To answer these questions, we have developed a framework so to guide our research within this framework. So we're interested in climate change impacts. So we start from global climate model projection or GCM projection. But these global climate models usually have resolution that's not high enough to resolve tropical cyclones. So we developed tropical cyclone climatology model, so to downscale the climate model and also to generate larger samples of tropical cyclones for risk analysis. Those storms will be characterized by genesis or the formation, track, intensity, and size. And given these parameters, we can estimate hurricane wind, storm surge, and rainfall. And the most interested is compound hazards from surge and rainfall. At the same time, we consider other hazards that may be compounding with tropical cyclones. We talked about extratropical cyclones working with BRAN, and we talk about we also consider sea level rise, which will increase the baseline for flooding. And recently, we also study heat waves that may follow tropical cyclones. Those are the hazards information. And on the other hand, we study exposure and vulnerability of natural and built environments, and combining the hazards and vulnerability information, we quantify the risk, which could be characterized by, say, probability of failure of structures or present value of future losses in the area, population affected currently and in the future climate, and so on. To support risk management, we can improve our building code, incorporate climate change into building code. We can develop structures along the coastline to mitigate the risk. We need to consider the cost benefit. We can also use insurance as an important tool and public policy, and also need to understand people's risk perception, and so on. So today I'm going to emphasize on a few points. I'll talk about our TC climatology model, the hazards with emphasis on the compound hazards, and then I will particularly talk about the compound hazards from tropical cyclone and heat wave. And the connection between the two is the infrastructure or the power system. Considering if you have a hurricane causing damage to the power system, you lost the power and the air conditioning, and you have heat wave to come at that time. So what would be that probability and how that may change due to climate change? So that's a topic that involving hazards and the infrastructure system. So to start, why do we need to develop a TC climatology model? Historical data is very limited for tropical cyclones for any particular location, especially high latitude like New York region. So we have always used monocolor simulation to generate synthetic tropical cyclones with these various characteristics, including track, intensity, and size. Currently, there are a few approaches. One is called a site-specific statistical method. For example, this is study to determine the design wind for the then tallest building in China, in Shanghai. So this is the 500 kilometer circle around Shanghai, and they look at all the historical storms coming to this region and develop distribution or joint distribution of these characteristics, and then draw samples from this distribution to generate a large number of synthetic storms based on these statistics. So this approach has been used to determine the design winds for many of the tallest buildings and longest bridges around the world. And it's also similar to the GPM or joint probability method. The FEMA has been used to develop the flood map for the United States. So this limitation of this approach is that you have to have sufficient historical record in the location to start with. So that may not applicable to a high latitude region that we don't have much historical data to start with. So another approach is basin-wide statistical approach that you don't focus on the particular location, but you generate a storm track for the entire basin, and then you may get enough samples for the location of interest. So this generation is based on the historical storm track over the entire basin. This approach has been used to develop the ASE wind map for the United States. However, both of these methods do not account for the effect of climate change. The third method, the one that we've been using and most of the results today I'm going to present are based on, is the deterministic statistical tropical cyclone model developed by Emmanuel and others. So the model is to generate storm track according to the statistics of the environmental wind, and also generate intensity of the storm along the track using a deterministic model. And this is just a schematic related to the deterministic dynamics of the tropical cyclones. So we have been using this model to generate a lot of results that I'm going to present. However, we have also developed a model kind of in between these two approach. That is, in addition to based on the model on the physics, we also use historical track. So we developed a statistical model that's connecting the climate environment and the storm characteristics. So we can generate storms that respond to the climate change, but it's a statistical model, so that's relatively simple. So in this approach that we call Princeton Environment Dependent Probabilistic Tropical Cyclone Model, or PEPC, we developed statistical relationship between the TC environment characterized by a few important climate parameters that's relevant to TC development, and the TC characteristics including genesis, track, wind intensity, and outer radius if possible. And then we can calculate the radius maximum wind using complete wind profile, and then the pressure deficit using also the wind profile. So this way we can have these parameters physically connected. So specifically, the TC genesis model is a dependent Poisson process on clustering grids. I'm not going to talk about detail, but the idea is it's a Poisson model, but it's a regression that were performed on clustering grids to overcome some data issue. And then we have analog wind TC track model. So the storm movement depends on environmental wind as well as the historical pattern of similar storms. And then along the track, we have Markov environment-dependent hurricane intensity model, so that the storm intensity is determined by the atmosphere and ocean environment along the track. And then we have log normal distribution of the outer size, and the inner size, or the radius maximum wind, can be estimated from the wind intensity and the outer size. So to show you some comparison between observation, this is the intensity from observation on the left, and the simulated intensity over the observed track on the right. So you can see that we can capture the features of intensity that have high intensity in this region and low intensity in the high latitude and so on. Together we use this system put together to simulate large numbers of storms along the US coastline or over the Atlantic basin, and then we look at the storm that made landfall along the this coastline, separated into three sections. O is for the whole coastline, and then we have Northeast USA, Southeast USA, and then Mexico. Here we're showing the landfall intensity as function of return period. The black is the observation for 36 years. Red is simulation for 36 years with uncertainty bound. And then using our model, we could simulate 3,600 years of simulation shown in blue. So you can see that our model compares very well with observation, but we can simulate a lot of more storms to capture the extremes that's far beyond the historical record. And that's the point of such a model, to generate a lot of more storms that's beyond the limited historical record. So that is our TC climatology model that we have developed recently. But before that, we have always been using Karen Emanuel's statistical deterministic model. Here's just showing you an example that we can generate a large number of storms for any given location. So in this study, we simulated 5,000 storms for New York City, for example, under one climate condition in the historical climate. And then for the same climate model, we generate 5,000 storms for the future climate And then the red portion on each track is about 100 hours before and during landfall that were used for hazards analysis, including storm surge modeling. And then in this study, we used 4 climate models, and for each climate model, we generate this 5,000 plus 5,000 storms. So we can look at how risk changes from historical to future climate, and how the uncertainty, look at uncertainties among the different climate models. So those are the TC climatology part that we generate the synthetic storms. So go to the hazards part. We have a complete wind model, which is combination of existing inner wind model and outer model. So this is a existing theoretical inner model. So hurricanes, although it has a coherent structures, the physics in the inner core and outer region actually are different. So the inner model can capture the areas around the eye wall, but then it would be off in the outer region. So the solid line is the observation dash of the model for different categories of storms. And then the outer model can capture the outer region, but then cannot capture the inner region. So this complete model basically mathematically connect these two models or merge these two models so that we can capture both regions relatively well. And another benefit of this is that we could use this model to estimate radius maximum wind, given the maximum wind and out radial information, because radius maximum wind information is often missing. And it's correlated with maximum wind, so it's difficult to model it separately. So with such a wind model, we can estimate and coupled with the synthetic models, synthetic tracks, we can model wind, extreme wind for any given location. So in this example, we're showing the wind as a function of return period for Hangzhou, which is a city near Shanghai in China. So here we first compare the simulation with historical observation. Historical observation here is red, and the simulation is black. So we got very good comparison with historical record, which validate both the synthetic model and the wind model. And then we use that to project future. This is for the particular climate model. We look at how the wind will change from the end of last century to the early this century, mid of this century to the later of this century. As you can see that for given return period, the wind will increase over time. So we applied this analysis with 6 climate models. And in this study, particularly, we want to talk about how do we determine the design wind. Currently in building code, the design wind is based on return period. But now the return period, given a wind level, return period will be changing over time, or given a return period, wind will be changing over time. So we cannot design for given return period. So we propose that we should design for cumulative probability over the lifetime of structure, so to absorb the time variation. So here we're showing that different lifetime exceedance probability that corresponds to the original return period in the stationary condition, and then calculate the design wind and to compare with the design wind if you assume the stationary of the climate. And so you can see that most climate models would predict a much higher design wind compared to the stationary wind. So that this is to promote the building code committee to account for climate change in our next building code revision. With wind model, we can use the wind model to drive the hydrodynamic model to simulate storm surge. Storm surge is largely dependent on the wind and with some also effects from pressure distribution. So here we used a particular model called ASIC to simulate flood hazards from tropical cyclones along the whole US East and Gulf Coast. Here we're plotting the 100-year flood level at each coastal county based on unstepped climate of 1980 to 2005. So as you can see that we have much higher flood level in the Gulf region and Florida region as expected. And then we applied that to 6 SoMAS 5 climate models on the high emission scenario, and also account for projected sea level rise. So this is a future return period of historical 100-year flood level. So in the future, 100-year flood level will become less than 20-year return period level. And then in the Gulf region, and this region will become about 10-year event. At high latitude, it become like 1-year event. So what are the reasons of this dramatic change of the risk? So we consider the contribution from sea level rise and also the contribution from storm climatology change. So this is showing the contribution from the two at different each coastal county. So in New England, most of the effects is induced by sea level rise. So mainly if you account for sea level rise, you got it. But then as you go to a lower latitude, the contribution of storm climatology change will dramatically increase. And in Gulf of Mexico, the contribution of storm climatology change is comparable or even higher than the contribution of sea level rise. So in many studies of quantifying impact of climate change on coastal hazards or coastal flooding, consider mainly the sea level rise. So this study, we really highlight that in these regions, we have to also consider the potential change of the storm activity. And then about rainfall, for risk analysis, we always need to develop a really simple model. Here we use a physics-based TC rainfall model originally developed by Carrie and Manuel. Those are just the model. And so it's very simple. It considers the main mechanisms. Wind, the rainfall depends on frictional effects, topographic effects, stretching, which is storm velocity change, and then baroclinic effects and the radiative cooling. So this model is very simple. You can code it in MATLAB and runs very fast. And we compare it with the WRF model, whether in research and forecasting full numerical model, which has to be run on this cluster for half an hour or not 1 hour for an event. So here we'll compare this two events, Isabel and Irene. As you can see that this simple model captures the pattern we can get from the WRF simulation for both cases. This is a total rainfall. I'm gonna go quickly. So this is just looking at the rain rate profile, comparing the two. And the R-Clipper, another statistical rainfall model, is quite off in these cases. And we coupled these models with a hydrologic model to look at, the stream flow and compare it with observation. And both models have similar performance and high performance. That means we could use this TC rainfall model as we use WRF model in this case. But it's super simple, calculating 1 minute or less than 1 minute on the laptop. This is just another studies. Our studies to further evaluate this model. This is to comparing with observation for different cases. This is a particularly good case, ISIC, compared with stage 4 radar. And this is simulation. This is great. And this is annual average rainfall over a period of time from this simple simulation. And this is from TRIM satellite observation. So we can capture this important rainfall regions from compared to satellite. This is a zoom in for the Louisiana region. Again, this is stage 4 radar and the satellite TRIM, and then the TCR model of the simple model simulated for a period of time for the rainfall. So this is just to say that although this model is quite simple, it can capture the main rainfall mechanism in comparison with WRF and observation. So now we have wind model, rainfall model, and storm surge model. We can put them together to look at compound hazards. So here we're looking at the compound hazards between storm tide and rainfall fields. So here we are showing the simulated so-called joint return period of extremes. Well, here extreme we call is 100-year rainfall and 100-year surge. So this is a probability of getting 100-year rainfall and 100-year surge. And then what is the return period of such an event or joint return period? So on the top figure, that's this joint return period for such joint extremes under the historical climate. And you can see this is extreme events because the return period are quite long. For the high latitude region, it's like 1,000-year events, mainly because in this region, rainfall and surge are not really correlated. To get both extremes together would be very unlikely. But when we consider climate change and sea level rise, in the lower figure in the high emission scenario, the return period would dramatically decrease, note a different scale. So for the Gulf of Mexico, the return period will change from 200 to 400 years to 10 to 30 years. Mid-Atlantic, 300 to 600 years will change to 5 to 15 years. For New England, the events have over 1,000-year return period under the historical climate and become 5-year events at the end of the century, given the high emission scenario. So this is a dramatic change of the joint probability or joint return period. And we again look at what are the causes of the change. Here we look at the factors for different locations. We have frequency of the storm, rainfall change, sea level rise, storm tide change, the dependence between storm tide and rainfall, and the total climatology change is including all the changes due to the storm change. As we can see that the blue bar is the highest for all the locations. This means the storm climatology change is higher than the effect of storm climatology change is higher than sea level rise in all the locations when we look at this joint hazards, because the importance of change of the rainfall in the future climate. When the storm becomes stronger and then also they move slower, we have much big increase of rainfall. And the dependence between rainfall and storm tide will increase in the future. So that makes the change of storm activity a bigger contribution even compared to sea level rise when we talk about this joint hazards. And recently we look at all the three hazards, wind, rainfall, and surge, and also not only the compounding of different hazards, but also the compounding in time and space. How about if we have storms coming in short time, between short time periods, and also could be storms, extreme storms coming to impact even at different locations, but if they are separated into by very short time periods, that's going to be a very big impact. So particularly here, I want to highlight something we call grid swarm sequential hazards, is that what is the probability of getting a Katrina-like event and Harvey-like event in the United States within a short time period, say 15 days. So here we're showing the time between a Harvey-like event and a Katrina-like event as a function of return period on the different climate conditions. In the control climate, there's no such events. In our large number of simulations, we can't find Katrina type and Harvey type storms coming within, say, 60 days or 15 days now. We don't have such event. But in the future climate, we will have such events. And here we're showing that for considering only storm climatology change and also storm change plus sea level rise. So such event, two events happening within 15 days will have non-negligible probability in the future climate emission scenarios, high emission scenarios. This is just example of our simulation showing a Katrina type of storm that generate peak surge above 8 meters. And here we have a Harvey type of storm generating rainfall greater than 1,000 millimeter. And these storms were separated by 10 days in our simulations. So those are just showing some new emerging compounding hazards that we should prepare for in the future climate. So those are the compound hazards. And if we want to talk more about the impact, we need to talk about, the generated flooding. I don't think I have too much time, so I'm going to go a little bit quick. This is to study compound flooding for a particular location. Here is Capeview River Estuary in North Carolina. Those are the evaluation of the model. We couple the storm surge model, hydrologic model, rainfall model, inundation model to look at the compound flooding. So those are just the evaluation of the model. And then we couple that with future projection of the storms. We can quantify what is a 100-year flood depth, including rainfall and storm surge in this region under the historical climate and in the future climate. So as you can see that in the future, the risk will dramatically increase from the current. Another point is that we always model coastal flooding from storm surge, but in this study, we found that rainfall can also significantly contribute to the coastal flooding, although the dominant is storm surge, but rainfall can contribute significantly. So we should account for that when we want to really quantify the flood depth. Quickly talk about, we consider hurricane blackout heat wave. So 9 out of 10 biggest blackouts in the United States were caused by tropical cyclones. The heat wave is the top cause of mortality in the United States, and the heat wave has been projected to increase in the future. So what is the connection? That is, if you have hurricane causing damage to power system, and then you had heat wave, will be a greater impact. And that has not happened much in the historical record, but it has been happening in recent years. Hurricane Laura 2020 impact Louisiana, and a heat wave followed. So 8 died due to heat-related illness following the loss of electricity. The second year, 2021, again in Louisiana, we had Hurricane Ida causing power damage, 1 million without power, possibly for weeks, and here comes heat waves. And so as a result, 10 died in the New Orleans city due to heat without electricity. So we develop a methodology to assess hurricane blackout heatwave compound hazards resilience. So on the one hand, we calculate the heat wave from the climate projection and also simulate storms to calculate the wind, flood, rainfall from tropical cyclones. And on the left hand, we model the power system. So given the hazards, what are the impact or damage to the power system components? And then given the damage of the components, we have power flow model to simulate power outage. And then we have a restoration model. It's very important to consider recovery process. So we model the recovery process considering, recovery plans, resources, and priorities, and so on. So combining the two sides of simulations, we can project future hurricane blackout heatwave compound hazard risk. We first applied it to Hearst County in Texas, including large part of Houston. This is just a power system in that region. Here's showing our modeled percent of residents with power as a function of days of the TC landfall. So this point is a damage, and this curve shows a recovery. So this is comparison between simulation in red and observation in blue, so we can capture the two events in this area well. Here we're showing the probability of long-lasting heat wave as a function of days of TC landfall. So we have been having, we have a significant increase of the number of long-lasting heat waves following hurricanes due to climate change. In this case, again, high emission scenario. And then combining this two sides of analysis, we can quantify, say, percentage of residents facing at least one longer than 5-day blackout heat wave compound hazard over a 20-year period. So in the historical climate, this probability or this percentage is very, very low, negligible. But in the future climate, it's a dramatic increase, about 18 times increase because the baseline is very low. And it become a hazard that we have to really consider. So we also looked at some strategies. We can vary lines, but should do that strategically. Here we're showing reduction of the risk as a function of enhancement rate or the proportion of bearing lines. The green is randomly bearing transmission lines, and the red shows randomly bearing distribution lines. Those are the strategies we're currently using. But we propose that we should strategically bury transmission distribution lines to bury the sections that's closest to the nodes, and that would be most effective in terms of reducing the risk. So this is kind of a study that we learned from our study that there's a certain features of the system that we can make use of in order to more effectively reduce the risk. And recently we applied the method to Louisiana. This is a modeling for Hurricane Ida and then Hurricane Laura, and look at the spatial distribution of power distribution, power outage distribution from observation and simulation, and we got quite good comparison. And comparing the power system modeling with the synthetic models and hazards models, we can quantify here interruption hour by compound hazard. Compound means power damage and heat wave together as a function of return period in the historical climate in blue and the future end of the century climate in red. So it's a dramatic shift of the risk. Here we have a line here showing the 35 million hour, which is a compound hazard from Hurricane Ida. So that will be a 278-year event, and will become 8-year event at the end of the century due to climate change. And here again, we look at the factors, and we look at different factors. If we consider only sea level rise, it's not going to change the return period much, because in this case, Louisiana, we have to adopt to sea level rise, so assume they're adopting to sea level rise. But hurricane intensity will reduce return period to some degree, and hurricane frequency change will be another reduction. And then storm climatology is a combination of storm frequency change, intensity change. But the dominant factor is a temperature increase. Here we also test that if we assume storm frequency will not change, in this case, the model shows frequency will increase, but we hold it to not change, we can still have a huge reduction, of almost the same reduction as we consider frequency change. Just to say that uncertainty of frequency does not affect our conclusion here. That's the risk will dramatically increase. So that's actually what I want to cover today, and I'll leave you or come back to the framework that we have to always think about hazards or compound hazards and vulnerability together to quantify the risk and look for the risk mitigation strategies. Thank you, and I would like to take your questions.
Great. Thank you so much, Ning, for the
Thanks.
interesting seminar. Now I'm going to turn it open to everyone here for some questions. And we'll do them in order here as I see them. And I think I see Edmund first. So Edmund.
Hi, thank you for the great seminar. Yeah, this is Edmund Chan. So I have a question. The results you showed are largely based on the SSP 8.5, which hopefully is not that is not the most likely outcome. So as you are looking at extremes, I would expect those to really depend very strongly on the climate projection on the scenario that you look at. So if you use less extreme increase, how might that change your projections?
Thank you. Thank you for that great question. And in fact, our last paper in Nature Climate Change, the reviewer asked us this question, and so we added 4.5 emission scenario. And surprisingly, that when we look at the sequential hazards and joint hazards, this 4.5 case still give us dramatic increase. That was interesting finding. I thought it would be much lower effects, but still it's a significant increase, a little bit lower than 8.5, but not much. But they only differ at the most extremes. So if you look at most extremes, they differ quite much. But if you look at general hazards or sequential hazards, the difference between the two is really small. And recently, I didn't get a chance to add the results here. Is that when we look at this case, say these two curves are so separate, right? We already did 4.5. So 4.5 will go like this. So the 4.5 will be similar to the current historical climate at extremes, but it will be close to the 8.5 at, IDA's level. So if it's 4.5, IDA's return period would become 10 years rather than 8 years in 8.5. But for more extremes, it's going to be similar to no climate change effect. So what we think is because in the difference between 8.5 and 4.5 in this case is that 8.5 will have more of long, very long heat waves. So 4.5 still give us sufficient heat waves and duration to get the compound, but the 8.5 will give much longer heat waves that support most extremes. So the difference, I think, between the two is the most extremes.
Yeah, thank you.
Thanks.
Yeah, Keith.
Hey, Ning, great talk. Really enjoyed it.
Thanks.
I had really two questions. One's really short. Basically, that rainfall model that you showed seemed to perform extremely well. I was wondering if that code was in an open source environment that we could potentially use, because we do a lot of rainfall modeling, and it could be very a big improvement basically from what we see, what we've used in the past. So
yeah,
that's my first question. And then the second thing is with respect to the return period changes that you observed or that you modeled in the Gulf of Maine. Now, do you guys consider the extratropical transitions of these storms? Is that captured in the Markov chain Monte Carlo approach?
Okay, good point. So first question about the rainfall model. So the rainfall model is great in terms of capturing these features, but I just need to also clarify that this is a good example, a good comparison. So cases with extratropical transitions, cases that the rainfall are affected greatly by the large scale features are less well captured by such a simple model. So this models capture the rainfall very well for the healthy tropical cyclones that's not affected much by the large scale features. In terms of the code, it's generally available. It's not put public publicly available to download, but generally, if you're interested to use this model, you can contact us or contact Carrie Emanuel, who originally developed the model, and we're really happy to share that code.
Okay.
For the second question, that's also always a challenge with exotropical transition. So in these results are based on the Carrie Emanuel's model, and that does not model the exotropical transition. So in our model of TC climatology, we didn't explicitly model exotropical transition either, but it's a statistical model. So the data is in the training data is in the model. So hopefully that's implicitly included some of that effects. So exotropical transition, it is a challenge to talk about.
Thank you.
Yeah.
Any other questions?
Yeah, can I ask a quick question? And
Yeah.
apologize, Ning. I apologize if I missed it, but I'm going to go back to the maybe some of the kind of beginning part when we're thinking about changes in hazards, right? So you're kind of doing the hazard approach, which is great, but it kind of, you know, when we think about frequency, that the frequency of these storms, right? So when you talk to reinsurers, when you talk to industry, while they're really interested in the hazard component, most of the CAT models and aspects like that are really still focused on changes in frequency of such events. And I understand that at least, you know, Carrie's approach to the synthetic tracks, right, kind of focuses on this, you know, seeding based upon the environment that comes out of the CMIT models, right? You're basically seeding and you're seeing if the storms spin up into synthetic tracks. But this oftentimes assumes this constant seeding rate to generate the synthetic tracks. And I'm curious with the approach, and maybe I missed this, so I apologize if I did, but do you in your approach, do you make assumptions about the seeding rate, or have you explored, if you do, right, or if you use a constant seeding rate, have you thought about exploring what happens if we assume an increase in the seeding frequency or a decrease in seeding rates or seeds in the future, as a way to kind of explore the range of these kind of return periods within the context of potential large differences in frequency? I don't know if that makes sense.
Sure. That's a very important point on the seeding part. So in Emanuel's model, it's a random seeding and then natural selection. It's selected by the environment.
Yeah.
So in the future climate, if the climate is more supportive to the storm development, and then most seeds will be selected so that you will have increased frequency. So even though he used the same seeding rate for current and the future, you may still get increased frequency. In fact, his model always predicts increase of frequency.
Yeah.
Well, most other models predicts a decrease of frequency. For our model, our TC climatology model, PAP-C, we do have different seeding rate because we don't do seeding, we don't do random seeding, we do possum dependent possum process. So the possum model depends on the climate variable, including potential intensity, vorticity, central deficit, and so on. So if those environmental parameter changes in the future, the seeding will be changed in our model. And interestingly, that our model predicted decrease of the frequency.
Yeah.
Well, his model predicted increase of the frequency.
Yeah, I think that, of course, you know, your colleague at Princeton, Gabe Vecchi, this has, I think, become a very interesting area of discussion because, you know, the question is, you know, the vorticity and the climate models that you might be using to, you know, downscale. The question, you know, these are happening at that vorticity is happening at the finest resolvable scales in the model. And so to some extent, it actually is the scale of the model that's most sensitive to, you know, diffusion choices, physics parameterizations, you know, grid setups and numerics. And it's an interesting area because it seems that, okay, if our future projections are sensitive to seeds, that's it's a little scary because seeds are probably more sensitive to the models than the cyclones themselves in some cases. So it's just
Yeah.
And things, something that always is in the back of my mind and sometimes keeps me up at night about my own work.
Yeah, definitely. I mean, the frequency changes the final results, and this is an unknown point, right? At this point, we do a lot of sensitivity analysis to say if the frequency does not change, what is the result? And we, in one study, also show that rainfall hazards or risk will dramatically increase. But if we want to keep the rainfall hazards the same, we would require the frequency to decrease by 70%.
Yeah,
which is impossible. So that's another way to say the rainfall hazards will increase no matter what. So we have to study this scientifically, but on the other hand, have to just look at uncertainty in the downstream hazards projection. But great point.
Awesome. Thank you.
Yeah.
And actually, I had a similar follow-up of all these parameters you're looking at, sea level rise and rainfall. I mean, which are these, where do you think most of the uncertainty is coming from now when you look at these compound hazards? And it's probably a function of space and time, but I'm just trying to get a feeling because there's large uncertainties in sea level rise, and then obviously there's uncertainties in the models, CMIT models, which 6 CMIT models you pick, things like that. So how do you sort that out, or how do you describe that issue?
Yeah, my feeling is big uncertainty. Number one is different climate models. So I mentioned, I saw the emission scenarios actually was important, but then 4.5, 8.5, very close and in large range of the projection, unless it's most extreme. But the climate models, or given the same emission scenario, the different climate models can give us very different results, different directions sometimes. So I think number one uncertainty is why these different climate models give us different projection of tropical cyclones using the same tropical cyclone model. We're currently doing a studies to just look at the different parameters in the different climate models. We found that, for example, most models give similar projection of the parameters like potential intensity, like more thermal parameters, thermodynamic parameters are more, the models agree more, but they don't agree with dynamic parameters like shear. So the models have very different view of how shear will change in the future, and that will affect the storm development differently. So that's a climate model level. And then we found the second would be just Kevin just mentioned about the frequency projection in tropical cyclones. And so tropical cyclone model itself has a big uncertainty. But given, I think those are the two big ones. And given this, we have pretty good wind model. We have pretty good storm surge model. Give high resolution, you can get it very accurately. And then rainfall, we have some uncertainty for sure, but I think it's probably a lower uncertainty. It's spatial uncertainty rainfall, and we may not be able to capture things like extratropical transition and rainfall affected by the large scale features and so on. Sea level rise, we basically more applying the projected sea level rise. There are big uncertainty, but at least we know the direction sea level is rising, will rise. There's no doubt on that. So I think there is more of at least the direction is certain. Yeah, so I think most worry for me is the climate models, number one. So that's why we always use like 8 models, 7 models in order to look at uncertainty among models. And then we do bias correction on these models. And then we do model combination. The users, whoever wants to look at it may want one answer rather than 8. So we also often combine 8 models, given the different weights, depending on the accuracy on simulating the historical period, and also do bias correction on them. So, yeah.
No, thank you very much.
Sure.
I don't see any other questions, and we're coming up on the hour here. So let's thank Ning again for an outstanding seminar. Really enjoyed it, Ning.
Thank you very much.
And